couple of transform pairs, and also for circuit analysis, some techniques. I want to say in general, we covered simple poles, and those are something where they have the form over, a simple pole is A over S plus small a. All right, that's a simple pole. We know that actually comes from the simple transform e to the minus at times u of t. That's a simple pole, it's a simple expansion, all right? I mean, simple transform. If you have just u of t, these are ones you have to know. I know that's 1 over s. I'm not going to prove that again, right? Now, other ones that are common based on this. The first is t times e to the minus at u of t. You'll run into this all the time. And here's how I'm going to explain this, doing this by property. If I call this x of t, you would automatically say I have x of s right there. I have that relationship. Do we all agree on this? Mm-hmm. The way I think of this, well, what if this is really just t times x of t, isn't it? All right. First I see the transform pair, I understand. Then if I see a t next to it, I'm not going to go and integrate that thing to get it. But I'm going to use the property, and I know that is minus d ds of x of s, that x of s, right? You all follow the pattern? I want to make sure you do, because I know a lot of people, they drop blanks on what the progression is in the solutions, but this is a simple pattern. T times this, I know that is that. Therefore, if I put t times that, I look at this as simply x of t. Just take a derivative of that. That means it's going to be a over s plus a squared. You can do it yourself, but derivative of this is going to be minus a over s plus a squared times the derivative of the inside, right? And there's already a minus sign, so it's positive. Agree, class? Another one you run into all the time. This is the last one I'll write here, then I'll go to the next one. Is this: if you have, well, you're going to have to know the cosine of omega naught t u of t. The simple transform of that is going to be s over s squared plus omega naught squared. You're going to run into the s squareds plus omega naught squareds in the denominator all the time. And that's cosine. You also know that sine of omega naught t times u of t transforms as omega naught over s squared plus omega naught squared. That will allow you to solve any problems with s squared plus omega naught squared as the denominator, with or without the s. Do you all follow me on this? Now, after that, then we do this. Well, what if I have e to the minus at times cosine of omega naught t u of t? Some of these you know by heart if you've been doing the problems. But for this one, you again view that as a property. You're going to use a property. Here, I would say this is now my new x of t. Call it x of t. Scratch that x of t here. All right. And this is my new x of s, right? And then what I can do is say this. If that's the case, this looks like if x of t is cosine of omega naught t, this really looks like e to the minus at times x of t, right? Do you all remember that? Now, the property says if I have e to the minus at x of t, that's just x of s plus a. Do you all remember that, class? How many do? These are properties that you have to bury in yourself. You have to know them in your heart. You can't just scratch your head, oh, I wonder what that is. You have to have absolute confidence because we're going to be using these a great deal. And you cannot, and I warn you about this, keep cramming. Try to do it every Thursday night. You'll lose it, and then you'll really, really kick yourself because in the final exam, it's cumulative. You get no tables. You'll just fall on your face. You have to do this stuff all the time. And I mean, I recommend it every day, at least an hour, but at least 3 times a week for 2 to 3 hours. It's the only way to get this stuff. So I know that, since I know this property, cosine here goes to this, the only thing I do is take the s and replace it with s plus a wherever it appears over there. So that means this goes to s plus a over s plus a squared plus omega naught squared. You all follow me? And that, what this is that's this transform, this. S plus a over s plus a squared plus omega naught squared. Everybody got that? I'm laying it out for you. Exactly what I would tell. Want to know if my life depended on it, I had to do Laplace transform problems. These are the essence of what you need. Now by the same token, if you have minus e to the a times sine of omega naught t u of t, you know that's going to go to, again, now the x of t is that sine, right? So whatever the sine transform has, with an s, I replace it with s plus a. You all see this, everyone? I just come over here, I see the sine transform right here. I just replace, that's the omega naught. Now it's s plus a quantity squared plus omega naught squared. So that's another one. Now, I can keep on adding, and I don't, at some point you just realize that you don't need to memorize everything if you know the properties. If I did say I put t times that, just tell me what you would do.
Just take the derivative.
What would you do? You would put minus, right? Minus the derivative with respect to s of this. That's a very doable derivative, all right? It's something you can do. You can work that one out easily, but you have to know the property. It's got to like ring a bell in your head. Oh, a t times that, I know this one, bang, I got it. Just take the derivative. So you need to think that way when you're doing transform operations. Now, almost all of the partial fraction expansions will have of the form of either a simple pole, a over s plus a, then a double pole like this. It could be, I say a double pole. This is a double pole because it's to the power 2, right? It could be a triple pole, but a triple pole is just taking this function, t e to the minus at, u of t times t, all right? Then what you basically is take another derivative of that and throw a minus sign, and then you would have that one, follow me? Usually, third order poles you rarely see in this simple circuit analysis. You're going to see things where you have constants over s plus omega naught squared. They're easy to break out. You'll also get something where you have s plus a over s plus a squared plus omega naught squared. Now here, I got to talk to you about that for a second. A lot of times, it's not in that form. It's in the form of a quadratic, and you have to do something called completing the square. How many know what completing the square is? You use this continually in engineering. Completing the square is this. If I have something where I have s squared plus, let's go 4s plus 9, right? I look at that, it doesn't have the form if this is in the denominator of an s plus a squared plus omega naught squared. You all see that, it doesn't. But one thing I do know, that if I have s plus a squared plus omega naught squared, that becomes s squared plus 2a, right, s plus a squared, right? I forget omega naught, yeah, I can leave omega naught squared. Omega naught squared then plus omega naught squared. Now I just want you to see this. I've taken the way, the form found there, and I've done the squaring operation so it becomes that, all right? Please watch this. Now this is the key. When you're doing completing the square, the middle term right there, you divide by 2, and that becomes, you take off the s and you take this 4 and divide it by 2, that becomes your a. So this would be s plus 2 squared. You all see what I'm doing here? Now, the last term, which was 9, equals this. All right? Now, we know what a is, correct, class? So now we say that 9 is equal to, for this one, a is 2, right? A is 2 right here. Wait a second. I'm trying to say, this is what I'm getting at right there. There was 4 there, it becomes 2. A in this equation is 2 that I'm working with. Okay, everybody see this? So now I take that and I say a squared was 4 plus omega naught squared is this, therefore 9 minus 4, right? Or 5 is omega naught squared, or omega naught is equal to square root of 5. And then I would have this form. This is real important you see it. Now, several of the problems I gave you required you to do that, completing the square operation. Do you all remember this, class? And if you complete the square, then you can get this form, the s plus a, so it would be this plus, and then it would be 5. And that would be your denominator. How many see what I'm up to right here? All right. How many recognize this as part of the problems you had to do, right? That's one of the operations that was included in order to solve it, you know? Really? I gave you several problems with that. I don't know which ones they are off the top of my head, but I know I did. Now, I'm telling you the essence of the things you need to know about the transform pairs. The partial fraction expansions become trivial, really, most of them. They're not hard at all. I don't give you hard ones because it's stupid for me to do that. In the real world, you wouldn't be doing that. You would let a computer do that for you. All right, but you have to know the basics. Now, circuit analysis, and I want to go through this with, now we're going to go through, I've done the thing where you base, did you have a question? No. Well, I said we're really, when you're talking about no initial conditions, those are the trivial problems. You just put in an equivalent impedance for an inductor is what, SL, and for a capacitor it's 1 over SC, and just solve it the way you would any other problem, right guys? Now, if you have something that is not zero initial conditions, when you have a voltage on a capacitor and a current inductor, now I'm about to tell you how to do this. And I want you to just realize, I'm not going to fly through this, and I'll go through a few examples. But this, for some reason, tricks people, and I think I know why. You're used to doing these problems where you had just RC or just LC, and you memorized, if it was an inductor, it was the current through that inductor was K times e to the minus T over tau plus K2, right? K1, K2. And if it was a capacitor, it was the voltage, and it was just K1 e to the minus T over tau plus, K1 times e to the minus T over tau plus K2. You solve for the K's based on the initial condition and final state, right? All right, well, here's where it gets tricky. It's no longer that simple because now your solutions aren't simple first order equations. They're going to be higher order equations. And this is how we can do this in the S domain and completely circumvent the need to solve differential equations with integrating factors. Do y'all do any integrating factors still over in calculus? I mean, when you did? I hated those things, especially with second and third order equations. They drive me nuts how to figure out which one I should use. All right, now, circuit analysis, tricks of the trade in the S domain. That's awesome, these things, because really that's what it is, it's tricks. Things you learn after 30 years of suffering. So here's a couple of things you learn. First, anytime you have zero initial conditions, we're going to do, is there a problem you want to do that's got zero initial conditions? Just tell me. Anybody got one of those homework problems with no initial conditions, no voltage or current? You want me to do it?
I have another problem that's not a homework problem.
Yeah, sure.
Okay, so it's a normal circuit.
It's what?
Just a normal circuit, be it power and a resistor and an inductor.
Well,
You
just
just
let me
take it.
pick it. All right, you got a resistor in series with an inductor in series with a capacitor, and you got a voltage, it's 5 U of T, right? All right, here's what she's talking about. This is a beautiful problem. I love this problem. Plus to minus 5 U of T. I didn't plant that on it. There's a resistor here. What's the value of R?
Just R. It has numbers, but I didn't.
Well, I need to, if I'm going to get this, because see, you can get overdamped, underdamped, or critically damped. This is a second order problem. Give me the values in a second. Then it's got an inductor. I don't know what it is, Dr. B. I just want you to tell me something. All right, there's an L there and there's a C here. So this has an impedance. I'm just going to put the impedance in of SL, and this is 1 over CS, and there's no initial conditions, right?
Right.
And they want the voltage here. All right, I'll just write this out for you, but we'll show you what the actual answer is in a second. All right, now to do this, I got to first do this transform. You transform everything in the S domain. I've already taken care of the impedances of the inductor and capacitor, correct? What's this transform as, people?
5 over S.
5 over S. Now, that's a voltage. Sometimes you can put 5 over S volts just to make sure you keep your head on straight. It's not an impedance, it's a voltage. Now what I want to do is find the proportion of voltage here versus the entire circuit. It's a simple what? Voltage division, right? So what I do is say my V of S here is equal to the source voltage, 5 over S, right? Then it's times this impedance, which is 1 over CS, over the sum of the impedance, which is going to be SL plus R plus 1 over CS, right? Now that's absolutely right. Here's the thing I'm going to tell you need to do. We don't want any 1 over S powers, do we? That's a no-no, we can't deal with it. So we multiply top and bottom by S, because you see, we got a 1 over S here, you gotta get rid of it. Does everybody see what I'm doing? When you multiply by S, that goes away, that goes away. But then I get an SR, right? And I get an S squared L. Now the second thing is this. I want the highest power in the denominator, the term, the S with the highest power, to have a coefficient of 1. Got it, everyone? So now I'll divide everything by L, top and bottom. Got it, everyone? You with me? Divide top and bottom by L. Do you all follow me? If I do that, I get this, and I get this. Now some of you are already looking at this and smiling in your head because you say, oh, this looks very similar to something I've seen in one of my courses, at least I think you have. They name omega naught as 1 over the square root of LC, don't they? Y'all remember seeing that? Or you saw F naught. It's a resonant frequency. F naught is 1 over 2 pi square root of LC. One of the two of them you've got to be familiar with if you're an electrical engineer. That is a resonant frequency for an LC circuit, right? Anything with L's and C's in parallel or series, that's it. Correct, class? Now, I've got the form. And here's the trick. This can factor as 2 simple poles. It can factor as a double pole, S plus something to the squared, all right? And it can factor as 2 complex roots. The ones with complex roots become S squared plus omega naught squared. Got me on that, class? So now, on behalf of you, you can tell me what the actual values were for R and C and L. R
is 3 ohms, L is 1 Henry, and capacitance is half a farad.
All right, so this C is 1/2, right? All right, now let's take a look at this. That means C times L. C is 1. L is 1, C is 1/2, so that's that. And then 1 over that would be 2 here. Agree, class? That's 2, this is 2. There's nothing tricky. Next thing I'm going to take a look at is I have R over L. R is 3, L is 1, this becomes 3. Agreed? So, what does that factor as?
S plus 2.
S plus 2, S plus 1. Do you agree with me, class? This is a trivial one. This isn't the fun one. So now we're going to do this one because she brought it up, and actually it's a perfect problem. I wish I would have planned it, but I didn't. So now I'm going to come down here. I'm going to say this. I'm going to bring it up here. What I want to do is I want to get V of t. So now I'm going to come up here and say that V of S is equal to 5 over S, right, times 2 over S squared, or I'm going to just leave this S plus 2, S plus 2, S plus 1. Correct, class? And I'm going to take the 5 times 2 and put 10 here. This is not the fun one. I'll do the fun one in a second. Or I'll do a different one. Yeah. Now, when I do this, how many poles do you see? Just look at that. 3 poles. Let's do it. I'm going to call it A over S, right, plus B over S plus 2 plus C over S plus 1. The order makes no, it doesn't matter. There's no association with the solution. How do we get A, class? First, I cover it up, this S, single S, right? Because the pole is at S equals 0, and I cover it up, right? Then I evaluate the equation when S is equal to 0. Do you all agree with me? So that's 10 over 2 or 5. Does everybody agree with that? So just put a 5 there. Now I can do this easily. I know you're going to have to move down in your notes to do it. I'm just going through the process with you, and I'm not trying to be tricky on you. What's the next pole at? S equals -2. First, we cover the S plus 2 up. We evaluate the remainder. I see I have -2 times -1. Do you agree with me, class? And that would be 2, correct? So 10 over 2 is 5. Next is C. I need, the pole is at S equals -1, right? Cover this up. Evaluate when it's -1. I have -1 plus 2, right, is 1. Times a -1 is -1, right? So I have 10. You all agree with me, class?
Should be negative.
Yeah, negative.
-10, pardon me, -10, you're absolutely right. Just leave this plus or -10. Thank you. You agree with me? Now, these transform pairs you have to know. These are very simple ones. What does 5 over S2 go to in the time domain? Now this is going to be the V of t. Class? 5 U of t. Does everybody absolutely understand that, correct? 1 over S is U of t's transform. You can prove it. What does 5 over S plus 2 go to? 5 times e to the minus 2t u of t. Agreed, everyone? What's the next one?
-10.
Right.
-10.
Minus 10 times e to the minus t u of t. Now we're going to stop and think about this solution for a second. And I just got to explain something to you. Really, this was 5 u of t. Do you agree with me, class? That's something that turns on to 5 volts and stays 5 volts forever. Correct, class?
Yes.
Now, what do you expect the voltage on this capacitor to go to as time goes to infinity? What does a capacitor look like as time goes to infinity for a transient problem? An open circuit, doesn't it? If this is an open circuit, no current can pass, right? And therefore, all the voltage here is the voltage at the source as t goes to infinity. In fact, we have that, right? Now, the other two things are something that are just damped exponentials that die down. At t equals 0, where does this start? Take a look at this. At t equals 0, what do we have? We have 5 plus 5, 10, minus 10. It starts at 0. There were no initial conditions. We meet that, right? But then it does some crazy wiggle waggle that you almost half the time have to plot. Now, I can tell you right now, because the 5 right here and the minus 10 right here, this, I don't believe ever goes through 0. You can check me on that and plot it. I don't believe it does, but you can check. Is there a solution for this?
Not plotted.
Well, it's smart to plot them to get a look at them. If you're doing, you can do this real quick on, what's that? You can use MATLAB, you can use Python, you can use Wolfram Alpha, you can use, there's another stupid one there's a Plot Me or something like that. What's the other one that kids use? There's one that's just for plotting. Alex Jones knows all of it.
Desmos, maybe? Yeah.
Gizmos?
Desmos. DESMOS.
Something Plot Me or something like that. Anyway, I've never used it, but this kid just in class, what does it look like? Ching. Here. I think Wolfram Alpha plots them too. All right. Anyway, that's how you do that one. Did you have a follow-up question on that or not?
No.
All right. And is the answer given on this one? Or no?
Yes, that's.
But it's pretty straightforward, right? The big thing is this, transform that much. Right? Now, I wanted to do one with a non-zero initial condition. Sounds fair. But before I do that, I got to show you how to get them. So, by the way, that's a pretty nice problem, actually. It's a nice, simple problem. It requires you to understand factoring, and if you don't know how to factor the thing, you all know the quadratic formula, right? In high school, didn't you have to memorize that? And use it for about 1 billion problems you could care less about? In my day, there was no new math. We had to suffer and do 100 problems. It's like, oh, we got it, really. All right. By the way, I didn't say that in class, but if you have ax squared plus bx plus c, and you want the solution to make that 0, it's called roots, right? What does x equal?
Negative b.
Plus or minus the square root of b squared minus 4ac over 2a. That's the form you're used to saying. At least I'm used to saying. All right? Now, since all the time the highest power, the s squared term always is 1, a is 1. So it becomes that. All right? I always make the coefficient of the highest power 1. It becomes that. And that's the roots of the equation. That's for any of them. They can be complex, there can be two real, or it can be a double, right? Because if this term is 0, then you got a double pole, right? You got something where you basically have s plus a squared. Follow me, class? All right, now back to the problem. So when we take a look at what things look like when the initial conditions are present, and I'm going to do it with the voltage transforms only because that's the way it's almost all the time put. I want you to follow me on this. With an inductor, I have a voltage V of t, and that voltage is equal to L times di dt. This is I, right? That's in the frequency domain. Once I take a transform of that into the Laplace domain, then I get, let me put the I of t up above it. When I take a transform, then I get V of s is equal to, and it's really going to be L times the quantity S, I of s, minus I of t equals 0. Or just put 0 in here. They put 0 plus, 0 minus 0 plus, doesn't matter. It's the value of the current at t equals 0. Now, typically, you say V of s is equal to S times L times I of s minus I at 0 divided, or times L. So what does that look like? Now, just follow me on this and you'll get it. What you're going to say is this, that if I have a current here, I of s, and I'm flowing it into an inductor here. Let me do it this way. An inductor here, it will develop a voltage that will look like this. It looks like this has the impedance SL, and put a Z down there. So to get this voltage on this part, the actual voltage right here would be equal to SL times I. You got me on that? But it also looks like that there's actually a fixed voltage right here that's going to be minus I naught times, I naught 0 times L. And actually, I've got the polarity wrong. The voltage here would be plus to minus that. This is going to be minus to plus because it is a minus voltage. And this voltage here is going to be L times I of 0 minus. All right? So the voltage from here to here is this voltage. All right? And you find it by thinking of this as an impedance right here and multiplying it times I. So the voltage here is it's SL times I of S plus L times I naught. You all see that? Now it takes a little time to do some problems with this before you can appreciate it, because you're not used to putting voltage sources in there that have a weight to them, times L. You're just not. And it's a voltage source, it's not a current source. You all with me on that? The next thing is if you have a capacitor. If I have a capacitor here, all right, now I know that if this is I of t, and this is the voltage, V of t, that's C times, did it backwards. I of t is equal to C times dV dt. Does everybody agree with that? And that capacitor has a value C. Class, or, just give me a show of hands. How many are very familiar with this? This should be just, it's like, an automatic reflex with engineers. It's like V equals IR kind of stuff. You have to know this extremely well. I cannot overemphasize that. So do the transform of this. Take the Laplace transform. You get I of s, right, equals to C, and then take the transform of dV dt. You get S times V of s, right? And then it's minus V of t equals 0. Now that's the time domain voltage evaluated on the capacitor at 0. Agreed, class? Now, what is typically done is you solve for Vs. I want a V of s in this problem. I want to show what the capacitor looks like in terms of a voltage. I don't want to do the current one for a reason, because it's more awkward, to be frank, in my opinion. I suppose there's people who find it more easier, but it's not easy for me. So when I find V of s, first thing I have to do is multiply through by C here, so I get C times, or SC times V of S minus C times V of 0 is equal to I of S, right? I'm just multiplied through. Then I take that minus C times V naught to the other side. So it becomes plus C times V naught. That's time domain. You might want to put a plus there to kind of encourage yourself to think time domain. But the 0 does it for me. Then you divide everything by SC. And that means that V of S looks like V naught, or it actually looks like I of S divided by SC plus V naught of 0 plus divided by S. And what you can do is think of it as this. You think of a capacitor as having an impedance here of 1 over SC. We're assuming an I of S is coming. So the voltage across here, the actual voltage across just that capacitor, would be equal to I of S divided by SC. Are you with me on this, class? Then you put the voltage source. This voltage source is additive, so it's a plus to minus. It has the same form of the polarity that's across the same sense of polarity as the capacitor. It's plus to minus here, and that voltage is just V naught over S. All right? Everybody got me? Now, whenever you're doing problems that have initial conditions, then when you replace the element, right, you don't just put 1 over SC, you put 1 over SC plus a voltage source, V naught over S, in series with it. Got me? And if you replace an inductor, then you put a voltage source that's SL impedance, all right, but it has also a voltage that's going to be L times I, but it's notice the polarity is opposite here, the sense of polarity. Got me on this, class? So now I'm going to do a problem, a transient problem. Something that you're pseudo familiar with, at least I think so. Well, maybe not. I don't want to do just a simple one. I want to do, well, I could actually. We'll start with a simple one. So for this one, I'm going to do this. It's going to be, why not? I'm going to put plus or minus 5 volts there. This is like a Dave Irwin problem. Got a switch that's going to flip it to equal 0. Then I'm going to put a resistor here, R, make it, say, 1 ohm, and a capacitor C, make it 1/2 farad. And I want the voltage across this capacitor, so I want plus to minus V of t. But I'm going to say VC, the voltage on the capacitor at t equals 0, is going to be 1 volt. All right? Capiche, everyone? All right, now we're going to do the problem. I'm going to go ahead and put this into the Laplace domain. And the first thing I do is, this is a crafty little trick. I replace this thing right here with a function that I understand. What am I going to use, class?
U of t.
5 u of t. And that's exactly what you do in the real world. You would just say, this is really, operationally speaking, just plus to minus 5 u of t. Do you all follow me? Now next, I do the I'm going to do the Laplace transforms of everything. Got me on this, class? Now please, would everybody be okay having this quiz on Monday? If you would be okay with it, give me a show of hands. The reason is I want to do some more circuits problems, and I think I've exposed you to circuits problems, but not the level I want to. So just bear with me, all right? So this becomes 5 over s, correct? Because I don't want to have to rush through this all the time. 5 over S. R is just R, right? It's 1 ohm, period. This is the impedance domain, so it's 1 ohm. Leave it as 1 ohm. Now this becomes what? Now think about what it becomes. This is going to be 1 over SC, right? Now that's the impedance, think impedance, but then there's a voltage, that's what the impedance of this is. Then there's a voltage source, but it's plus to minus what? 1 over S, correct class? Do y'all remember I just put that up there? If you don't, look at your notes. You see it's going to transform as V naught over S. And the polarity is the same as the polarity here. So this is just 1 over S, because the voltage was 1, correct class? But make sure you say this is a voltage. Make sure you say this is a voltage, not an impedance. Because what people do is look at it as an impedance. It's not, it's a voltage source. Understand? How many of you see what I'm doing so far? Pay attention to this, because this is good stuff. And this is where you're going to start really appreciating some of this stuff. You're going to see the application to circuit analysis. And there's a lot of applications. And wait, when I was when you were sitting where you were, God, that's a long time ago, but the one thing I can tell you it was really hot was high fidelity sound. They had quadraphonic. The Who came out with quadrophenia. If you had a quad player, it sounded amazing and stuff like this. I know you got what? You got surround sound 5-to-1, 5-1, or you got a subwoofer and basically quadraphonic sound now. But high fidelity sound was really, really in, and it was cost a fortune. But when you got done with this course, I'm just going to throw this in here to give you a little incentive. What you learned is all the tricks of the trade. So when you had this in your amplifier design courses, you could build amplifiers that would cost thousands of dollars for pennies on the dollar, literally for under 50 bucks, 100 bucks for all the parts, and you just rip the transformer out of some junk piece of equipment, and they're all over the place. And that's what really costs money with amplifiers, the transformer. So that's when you get the power boost. So we'd make amplifiers. They had 100 watts RMS per channel. Flat. I mean, the intermodulation distortion, nothing. The interharmonic distortion, nothing. All the measures of fidelity you basically over-designed for because you didn't care if it cost an extra component. You know, who cares? You basically, your components are dirt cheap. I got a shop right there. They sell them to you for pennies on the dollar for what they really cost. And man, when you saw what you could do, it really hit home. Designing amplifiers to do all sorts of stuff. But where it really paid dividends was the guy. How many know what Bose speakers are? Bose was a professor at MIT. And when he came out of grad school, and one thing he noticed, he couldn't buy a decent set of speakers for under $1 million. It cost a fortune. But one thing he did is, he's a smart guy, he looked at the actual output power versus frequency of a speaker. I mean, any speaker would do something like this. Well, what you want ideally is flat. Any input power, same output power. That's called fidelity sound. That's without distortion. So what Bose did was got some cheap speakers. He saw this was their curve. He inverted that, took this, created a system that multiplied before it went to the input of the speakers by this function, and he had perfectly flat sound. And the distortion, he could actually invert this distortion. So he had an active crossover in the 901's first sets of 901 speakers. And they were amazing, and they were dirt cheap relative to, I mean, I don't know if you know how much speakers cost. High fidelity speakers can go $25,000 for one, just one. If you look at some of these sound systems that the Stones and stuff use, they're unreal expensive. All right, but he made this stuff dirt cheap. And then when I saw what I was being taught, what it could do for me, I really started appreciating it. We built our own amplifiers. I had one guy, I think he built them out of concrete, speakers out of concrete, because they don't bend or flex, so the sound is incredible. The drivers are still expensive though. Those are the actual speaker cones that move. They cost some money. I don't know if the prices have gone. Has anybody ever tried to build speakers or stereos or anything in here? Nobody? Anybody, any ham radio operators in here? Any hackers in here? Do I have any? Well, you wouldn't tell me, would you? Anyway, I'm trying to get a feel for who you are so I can try to tailor my lecture to you, your needs, your interests. But it was my interest back in the day, high fidelity sound. I found this course could do a lot for my design. So anyway, back to this thing. So what is this output V of S? All right, that's what we're after. Now here's how you get it. I want you to listen to me carefully. The mistake is saying, well, V of S is just the voltage. We'll use voltage division. People will say that's an impedance. It's not an impedance. It's a voltage source. So how would you do this normally? Well, you would find the net current, wouldn't you? You would find the net current flowing this way. And then once you had that net current, you would multiply it by that impedance, correct? Then you would have the voltage there, and you would add this voltage to it, wouldn't you? Do you all agree with me, class? So we're going to do that. What is that net current? Well, how would you do it if this was, if this was a 2-volt source and this was a 5-volt source? You would take 5 minus 2 is the net voltage that's driving the current and divide it by the net impedance, correct, class? So we do it the same way. We're going to say, well, the voltage that's overwhelming is the 5 over S, right? And we're subtracting from it this one that's opposing it, the 1 over S. That's my net voltage. That's 4 over S. That's what's driving this guy. Agreed? Now, what's opposing this guy? This is, I should say, this is not I of S. It's actually the voltage. I'll call it V prime of S. That's the voltage driving it. The current I of S would be equal to that 4 over S, the next voltage, divided by, and it would be 1 over SC. I'm going to make C equal to a half, right? I said it was 1/2 somewhere. So that would be 2 over S plus 1. And does everybody see what I'm doing here? I'm taking the net voltage that's driving the current around the loop, and I'm dividing by the net impedance that's preventing it. And this has nothing to do with it. This is a voltage source. I'll say that again and again until you get sick of it. Agreed? Now, once I have that current, yeah?
Where'd you get that 2 at the top from? I thought that's.
Well, if this is 1/2, it's 1 over CS, and C is 1. C is, I put C is equal to 1/2. I'm sorry, I erased it. All right, so now what I'm going to do is multiply top and bottom by S. All right. Now I have I of S, correct? Everybody got me? Now I'm going to get V of S. Oh, so V of S is equal to, well, it's going to be equal to that current times 1 over SC, right? Because the impedance of this is 1 over SC, so the voltage here will be 1 over SC times the current. So it's going to be 4 over 2 plus S times 2 over S, right? And then I have to go ahead and say it's also, what's going to add on to this is 1 over S. I hope you appreciate what I'm doing. You with me on this, class? So now I've gone ahead and I've got the output voltage in terms of the S domain. I'm going to go through the mathematics on this one. I can see that this one just goes to U of T, correct, class? But I'm going to do a partial fraction on this. So I have 4 over S plus 2 times 2 over S, and that means 8, right? That's 8 over that, and I need that to go to some A over S plus B over S plus 2. I'm just restructuring this a little. Agreed, everyone? I mean, do you all see it on this one? All right, it's partial fractions. What's A? What's the value? Wait a second.
Don't you have another S in the denominator?
I'm sorry, this is 5, isn't it?
8.
8? I'm sorry, this is 8, my bad. So what's A? Close this up, right? Cover up the S, 1 over S pole on that side, and evaluate that at S equals 0, correct? Do you all agree it's 4? I want you to make sure you see it. 8 over, that's 2, is 4, correct? So that's 4. What's B? Cover this up, let S equal minus 2, it's, pardon me? Minus 4. I'm just making sure everybody sees this. Minus 4. Now, I'm going to replace, or I'll rewrite this. So this is equal to 4 over S minus 4 over S plus 2 plus 1 over S. Y'all see what I'm doing? I've just gone ahead and I've put in the expansion for that. right? Partial fraction expansion. Y'all with me? All right. Now, does anybody see an easy grouping? About 4 over s and 1 over s is? Not 3 over s. 5 over s.
Heard it wrong. I just saw the minus
Don't-
sign as you said.
Yeah, it's all right. All right, now, can y'all go backwards into the time domain? All right, what happens? What's my v out of t gonna be? Well, what does this go back as? 5 u of t. What does this go back as?
Negative 4 e to the negative 2t.
2t u of t. Y'all see it? Let's talk about this for a second before we move on. You always want to evaluate things at their initial and final state to make sure you didn't mess up. The initial state was the voltage was 1 volt at t equals 0, right? Is it? So when t equals 0, right at 0 plus, right? That's 5 and this is 4 because e to the 0 is 1, right? 5 minus 4 is 1 volt. Checks that box, right? Where does it go to as t goes to infinity? That's a capacitor. It always goes to, that becomes an open circuit, right? In a series circuit, it goes to the series voltage, which is 5 volts. Does it? Yes, checks both boxes. That's how you do the problem. Using the initial conditions for the capacitor. For the inductor, it's very similar, except what? The polarity switches, doesn't it? And it's multiplied by L. It's the initial current and it's multiplied by L. Now when you do a few more of these problems, it'll stick with you. It's not hard. But I'm going to tell you one thing. The mistakes that I will be seeing, almost guaranteed, is this, we thought it was an impedance. I'm telling you this, put a warning sign. This is not an impedance, it's a voltage, all right? That's important. And I just use the voltage ones, don't mess with the capacitor, the parallel. They have the current ones. You know how I can use Thevenin Norton equivalent? You can do a Norton's equivalent or source transform for this. Don't do that. Just leave it with voltage, please. It'll save you. Now, questions. I got about a minute or two, right?
Yeah, 3.
3. I got 3 minutes. Fantastic. Who's got one? Yeah.
Can you re-explain after you did the 2 over s plus 1 over s, like the stuff you just started to erase?
Oh, how did I get that?
Yeah. Like with the split of the.
Well, here's what I had. You're asking, I had 5 over s plus, what was it? 4 minus 4 over s plus 2, right? Isn't that right?
You wrote it 2 over s instead of the 4 over s.
Okay.
Yeah, you wrote a number wrong.
I did?
V of s should be 4 over s plus 2 plus 1 over s, or negative 4 over s plus 2 plus 1 over s plus 4 over s. You have 2 over s in V of s.
Hold it. Help me out. Here?
V of s, yeah. You have
All right,
2
hold on.
over s.
Whoa. All right, what do I have wrong?
You have 2 over s, it should be 4 over s.
Ah, this?
Yes.
No. Oh, that is 2 over s.
4 over s comes under the partial fraction expansion.
Right.
That's 2 times 4 is
before
8.
partial fraction.
It's
Oh,
8.
that's before that. Oh,
Yeah.
okay.
Yeah, that's okay. But what are you asking for? You asking for this? How do I get
Yeah,
that?
like after that, how'd you get to the,
From this part or not?
from that part?
All right, here's what I did. I took these two and I did a partial fraction expansion.
Okay.
All right, if I do a partial fraction expansion, the poles are a over s plus b over s plus 2. Then I figured out what a and b were.
Okay.
And then once I did that, I saw I have a 1 over s, I added those 2 terms.
Okay.
Understand? And then, and it became 5 over s.
Okay.
So where did the minus come from for b then?
Because when you do the partial fraction expansion, the second term has it's minus, this is minus what, minus 4 over s plus 2 when you do partial. You want to, here, just look here. If I want to calculate what b is, now listen, I cover up this part, right? And I evaluate everything left, not this, but there, at s equals minus 2, right? When it's minus 2, what do you have? 8 over minus 2 is minus 4. That's it.
Okay.
Right, so
I know you gotta go to Parker or someplace in outer Wisconsin. I'm gonna give you some more homework. I'm gonna give you a quiz, same stuff, all right? All right? It will not have initial conditions on this one, but do the problems with initial conditions. At least I don't think it will, unless I get in a bad mood on Sunday. No, I'm kidding. It won't. And, you know, game day is here for the basketball game against Kentucky, right? How many are going? 1? Kentucky is a big game down here, brothers and sisters. I wanna, if I can get tickets, I'm going.
Can you, like, maybe in the group meet, like,
Do you have time? Oh, you gotta go to class. Can you see after class?